Welcome back. Over the last few episodes, we built orthogonality, projection, and the QR factorization. Today, they pay off in the most beautiful theorem in linear algebra, the spectral theorem. It is about a special family of matrices, the symmetric ones, the matrices that equal their own transpose, so the entry in row I, column j always matches the entry in row j, column I. For a general matrix, eigenvalues can be complex and eigenvectors can point every which way. But for symmetric matrices, three wonderful things happen at once. The eigenvalues are always real, the eigenvectors can be chosen perpendicular to each other, and the matrix factors as Q times lambda times Q transpose, where Q is an orthogonal matrix and lambda is diagonal. We will prove why, see the geometry, pure stretching along perpendicular axes, and finish with positive definite matrices and the quadratic forms they control. Let's begin. Let's pin down the object. A square matrix is symmetric when it equals its own transpose. Concretely, that means it is a mirror image across the main diagonal. The entry in row I, column j, equals the entry in row j, column I. The diagonal entries can be anything, but each off-diagonal entry has to match its reflected partner. So a 2x2 with a 2 and a 3 on the diagonal and a 1 in both off-diagonal slots is symmetric. Why care about this family? Because symmetric matrices are everywhere. For any matrix A at all, the product A transpose times A is symmetric, and so is A times A transpose. That fact alone drives the next two episodes. Covariance matrices in statistics are symmetric. The Hessian of second derivatives is symmetric. Networks of springs, electrical resistances, and graphs all produce symmetric matrices. When a matrix encodes a mutual, two-way relationship, it tends to come out symmetric, and symmetry, as we are about to see, is an enormous gift. The first promise, every eigenvalue of a real symmetric matrix is a real number. Here is why in outline. Suppose A times x equals lambda times x, and for now, let's allow x to have complex entries, since we do not yet know lambda is real. Multiply on the left by the conjugate transpose of x. On the right, we get lambda times the conjugate transpose of x times x, and that quantity is just the squared length of x, a positive real number. Now look at the left side, the conjugate transpose of x times a times x. Because A is real and symmetric, this number turns out to equal its own complex conjugate, and any number equal to its own conjugate must be real. So we have a real number on the left, and lambda times a positive real number on the right. Dividing, lambda has to be real. The punchline, symmetry forbids the rotational complex eigenvalues that general matrices can have. A symmetric matrix never secretly rotates. The second promise, eigenvectors for different eigenvalues are automatically perpendicular. The proof is a small, elegant trick. Take two eigenvectors, x with eigenvalue lambda and y with eigenvalue mu, and suppose lambda and mu are different. Now compute the quantity x transpose times a times y in two different ways. Reading it one way, a acts on y to give mu times y, so the whole thing is mu times the dot product of x and y. Reading it the other way, we move a onto x, and here's where symmetry enters, because a transpose equals a. So a acts on x to give lambda times x, making the whole thing lambda times the dot product of x and y. We now have one number equal to both lambda times the dot product and mu times the dot product. Subtract lambda minus mu times the dot product is 0. Since lambda and mu are different, the dot product must be 0. The eigenvectors are perpendicular, and when an eigenvalue repeats, its whole eigenspace can be handed an orthonormal basis of its own. Before we state the theorem, meet the matrix that will play a starring role, the orthogonal matrix. A square matrix Q is orthogonal when its columns are orthonormal, perpendicular to each other and each of length 1. The compact way to say that is Q transpose times Q equals the identity, which means the inverse of Q is simply its transpose. That single property has wonderful consequences. An orthogonal matrix preserves length. The length of Q times x equals the length of x. It preserves angles and dot products too. And its determinant is plus or minus 1, plus 1 for a pure rotation, minus 1 when a reflection is mixed in. Geometrically, an orthogonal matrix is a rigid motion of space. It can spin and flip, but it never stretches or shears. Remember from the spectral theorem that we collect the perpendicular unit eigenvectors of a symmetric matrix as columns. Those columns are orthonormal by construction, so they assemble into precisely such an orthogonal matrix Q. That is why the change of coordinates in the spectral theorem is a pure rotation. Now assemble the pieces. We have real eigenvalues and a full set of perpendicular eigenvectors. Scale each eigenvector to unit length and place them as the columns of a matrix Q, because the columns are orthonormal. Perpendicular and length, 1. Q is an orthogonal matrix, meaning Q transpose times Q is the identity. Its inverse is simply its transpose. Then the diagonalization A equals Q lambda Q inverse becomes A equals Q lambda Q transpose, where lambda is the diagonal matrix of eigenvalues. This is the spectral theorem, and it is the cleanest factorization in the subject. There is an equivalent and very revealing form, A is the sum, over each eigenvalue of that eigenvalue times the outer product of its unit eigenvector with itself. Each outer product is a projection onto an eigendirection, so a symmetric matrix is literally a weighted sum of projections onto perpendicular axes. And here is the deep fact: a matrix is orthogonally diagonalizable if and only if it is symmetric. The two notions coincide perfectly. The factorization is not just algebra, it is a complete geometric story. Read A equals Q lambda Q transpose from right to left, acting on a vector. First, Q transpose rotates space so that the eigenvectors line up with the coordinate axes. Second, lambda stretches, each axis gets multiplied by its eigenvalue, lengthening or shrinking it, and flipping it if the eigenvalue is negative. Third, Q rotates everything back to the original orientation. That's it. A symmetric matrix does no shearing and no genuine rotating of its own. Stripped to its essence, it is pure stretching along a set of perpendicular directions called the principal axes, the eigenvectors, and the amount of stretch along each axis is exactly the corresponding eigenvalue. This is why symmetric matrices feel so rigid and well-behaved. A circle under a symmetric matrix becomes an ellipse whose axes point along the eigenvectors and whose radii are the eigenvalues. Geometry has been reduced to a list of perpendicular stretches. Here is the geometry on one canvas. On the left, a unit circle, and through its center two perpendicular arrows, the unit eigenvectors Q1 and Q2. Notice they point in tilted directions, not along the horizontal and vertical axes. The matrix gets to choose its own preferred directions. Now apply the symmetric matrix A. The circle becomes an ellipse, shown on the right. And here's the whole point. The major and minor axes of that ellipse lie along exactly the same two perpendicular directions, Q1 and Q2. They did not tilt, they only stretched. The semi-axis along Q1 has length lambda1, and the semi-axis along Q2 has length lambda2. The eigenvalues are the radii. A general matrix would have twisted those arrows out of perpendicularity, but symmetry keeps them locked at a right angle. Stretch along fixed perpendicular axes, nothing more. This single picture is the spectral theorem made visible, and it is the seed of the singular value decomposition coming next. Among symmetric matrices, the nicest are the positive definite ones. A symmetric matrix, A, is positive definite if the number x transpose times A times x is strictly positive for every non-zero vector x. There is a clean test using the spectral theorem. A symmetric matrix is positive definite exactly when all of its eigenvalues are positive. If we allow eigenvalues to be zero as well, we get the slightly weaker notion called positive semi-definite. Here is why the eigenvalue test works. Switch into eigencoordinates by setting y equal to q transpose times x. The quadratic quantity x transpose ax then becomes a clean sum, each eigenvalue times the square of the corresponding new coordinate. A sum of eigenvalue times a square is positive for every non-zero input precisely when every eigenvalue is positive. So positivity of the form and positivity of the eigenvalues are the same statement. Positive definite matrices also have positive pivots and elimination, positive leading minors, and a square root style factorization called Cauchy. They are the matrices that behave like genuine upward curving measures of size. Positive definiteness is really a statement about a surface. A quadratic form is the function that takes a vector x and returns x transpose times A applied, that is, x transpose ax, a single number built from products of pairs of coordinates with asymmetric. By the spectral theorem, rotating into eigencoordinates turns this tangled expression into a clean sum of squares, each eigenvalue times the square of a coordinate. Once it is a sum of squares, the shape is dictated entirely by the signs of the eigenvalues. If every eigenvalue is positive, the surface is an upward bowl with a minimum at the origin. That's the positive definite case. If every eigenvalue is negative, it is a downward dome with a maximum. And if the eigenvalues have mixed signs, you get a saddle, curving up in some directions and down in others. The level sets, where the form equals 1, are ellipses when the matrix is definite and hyperbolas when it is indefinite, and in both cases their axes point along the eigenvectors. The eigenvalues are the curvatures. The eigenvectors are the axes. Here are the three shapes a quadratic form can take, side by side. On the left, both eigenvalues are positive, and the surface is an upward bowl with a single lowest point at the origin, the positive definite case. Along every direction you walk away from the center, the surface climbs. In the middle, the eigenvalues have mixed signs, and the surface is a saddle. Walk along one principal axis and you go up, walk along the perpendicular one and you go down. That is the indefinite case, the shape of a mountain pass. On the right, both eigenvalues are negative, and the surface is a downward dome with a single highest point, negative definite, and upside-down bowl. In all three pictures, the two perpendicular lines on the floor are the eigenvector directions, the principal axes, and the steepness of the surface along each one is governed by that eigenvalue size. Read the signs of the eigenvalues, and you instantly know the shape. All positive means a bowl, all negative a dome, mixed a saddle. Let's diagonalize a concrete symmetric matrix, 2's on the diagonal, 1's off the diagonal. First, the eigenvalues. The determinant of A minus lambda times the identity is the quantity 2 minus lambda squared minus 1 set to 0. That factors to give lambda equals 3 and lambda equals 1, both real as the theorem promised. Now the eigenvectors. For lambda equals 3, solving gives the direction 1, 1 normalized, that is 1 over root 2 times the vector 1, 1. For lambda equals 1, the direction is 1, negative 1 normalized, 1 over root 2 times the vector 1, negative 1. Check their dot product, 1 times 1 plus 1 times negative 1 is 0, perpendicular, exactly as guaranteed. Place these two unit eigenvectors as columns to build Q, and put 3 and 1 on the diagonal of lambda. Then A equals Q times lambda times Q transpose. The matrix has been rebuilt as a rotation by 45 degrees, a stretch by 3 along one diagonal and by 1 along the other, and a rotation back. Now let's read the shape of a quadratic form. Take f of x and y equals 2x squared plus 2xy plus 2y squared. To write this as x transpose ax, put the coefficients of x squared and y squared, both 2, on the diagonal, and split the cross-term coefficient 2 evenly as 1 and 1 into the off-diagonal slots. That gives exactly the symmetric matrix from the previous example, 2's on the diagonal and 1's off it. So we already know its eigenvalues, 3 and 1. In eigencoordinates, the form becomes 3 times the first coordinate squared plus 1 times the second coordinate squared, a clean sum of squares. Both eigenvalues are positive, so the form is positive definite, and the surface is a bowl with a strict minimum at the origin. Its level set, where f equals 1, is an ellipse. The long axis points along the direction 1, negative 1, the small eigenvalue, where the surface climbs slowly, and the short axis points along 1, 1, the large eigenvalue, where it climbs steeply. Let's classify three symmetric matrices by their definiteness. Case A, a diagonal matrix with 3 and 5 on the diagonal. The eigenvalues of a diagonal matrix are just its diagonal entries, 3 and 5, both positive, so this is positive definite. A bowl. Case B, 1's on the diagonal and 2's off it. Its eigenvalues are 3 and negative 1, mixed signs, so it is indefinite. A saddle curving up along one eigendirection and down along the other. Case C, all entries equal to 2. Its eigenvalues are 4 and 0. With one positive eigenvalue and one 0, it is positive semi-definite, a valley that is flat along one whole direction rather than a single low point. There is a fast shortcut for 2x2 matrices. A symmetric matrix is positive definite exactly when its top left entry is positive and its determinant is positive. You can verify that case A passes both tests, case B fails because its determinant is negative, and case C sits on the boundary with determinant 0. A little history. The story begins with the geometry of quadratic surfaces, ellipsoids, and hyperboloids. In 1829, Augustin Louis Cauchy proved that the eigenvalues of a symmetric matrix are always real, precisely while finding the principal axes of these surfaces. In 1852, James Joseph Sylvester discovered the law of inertia. No matter how you change coordinates, the number of positive, negative, and 0 eigenvalues of a quadratic form never changes. Through the middle of the century, Jacobi and Weierstrass turned diagonalization of forms into a systematic theory. Then, around 1900, David Hilbert extended the whole circle of ideas to infinite-dimensional operators and gave us the modern name, the Spectral Theorem. He called the set of eigenvalues the spectrum. And a beautiful twist, a few decades later, that same word and that same mathematics turned out to describe the actual spectral lines of atoms in quantum mechanics. The spectrum of a matrix became the spectrum of light. Let's recap. A symmetric matrix equals its own transpose, mirror symmetric across the diagonal. For such a matrix, three things hold together. All its eigenvalues are real. Eigenvectors for different eigenvalues are perpendicular, and a full orthonormal set of eigenvectors always exists. That gives the spectral theorem, A equals Q times lambda times Q transpose, where Q is orthogonal. Its transpose is its inverse, and lambda is the diagonal of eigenvalues. Geometrically, a symmetric matrix is pure stretching along perpendicular principal axes. Rotate to those axes, stretch each by its eigenvalue, rotate back, with no shear and no genuine rotation of its own. A symmetric matrix is positive definite when x transpose AX is positive for every non-zero x, which happens exactly when all eigenvalues are positive. And its quadratic form in eigencoordinates is a clean sum of eigenvalue times coordinate squared, whose shape, bowl, saddle, or dome is read straight off the signs of the eigenvalues. Next episode, we carry this perfect structure to every matrix in existence with the singular value decomposition. Today we found the most beautiful structure in linear algebra. A symmetric matrix is one that equals its own transpose, so the entry in row I column j matches the entry in row j column I. The spectral theorem says three things happen at once for every real symmetric matrix. First, all of its eigenvalues are real numbers, never complex. Second, eigenvectors belonging to different eigenvalues are automatically perpendicular. And third, you can always pick a full set of perpendicular unit eigenvectors that form an orthonormal basis. Put those eigenvectors in the columns of a matrix Q, and Q is orthogonal, meaning Q transpose times Q is the identity. Then the matrix factors as A equals Q times lambda times Q transpose, where lambda is the diagonal matrix of eigenvalues. This is called orthogonal diagonalization. Geometrically, it means a symmetric matrix is pure stretching along perpendicular axes. Rotate to line up with the eigenvectors, stretch each axis by its eigenvalue, then rotate back. We also met positive definite matrices, the symmetric matrices whose eigenvalues are all positive. These are exactly the matrices whose quadratic form, x transpose ax, is positive for every non-zero x, the upward bowls. The eigenvalues are the curvatures, and the eigenvectors are the axes of the bowl. Next episode, we take this miracle and stretch it to cover every matrix in existence, even rectangular ones, with the singular value decomposition. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching, see you in the next one.